I really appreciate you joining us today. Some of you over your lunch hour, so good morning, good afternoon, whatever it is for you. But I'm Matt Galeen. I'm the Applications Engineering Manager here at Tolomatic. So we really specialize in linear actuation and linear motion solutions, just in general. What I wanted to kind of touch on today was linear servo press technology and how you can unleash that in your manufacturing plant or in general. So one thing I wanted to start with is really touch on some key press technologies. And a big takeaway here is, this is a very broad brush stroke. There are certain things you can do on each one of these that is going to improve some of the highlights I've got here. So for example, in traditional hydraulic, I have it set as traditionally lower speeds, but you could build up pressure and achieve much higher speeds. So there are some ways around some of these. But just to kind of go left to right, you got your traditional hydraulic. Generally, that's more focused on extremely high force. You're going to have a little more limited moderating capability. It can handle quite a bit more shock capability. So an example there would be in a lumber environment. If you've got a heavy log that's rolling down and impacting into a hydraulic cylinder, that would be an example of a shock load. But in general, you're going to have a little lower upfront cost. There are added components because you've got that HPU or that hydraulic power unit that's shown on the left here. Kind of midway in between the two is your electrohydraulic. And again, this kind of combines some of the benefits of hydraulic with some of the benefits of the linear servo. So you maintain some of that shock capability from the hydraulic. You maintain that longer stroke, that higher force at the trade-off of, you still have some risk of fluid leaks and added components for potential failure modes. You do get a nice boost in energy efficiency over your traditional hydraulic, but not quite as much as the linear servo. So moving on to the right here, your linear servo, which we're going to be focusing on today, that's really more driving at, higher energy efficiency, more predictable service life. Generally, that does also come with some downsides, right? So you have a certain amount of stroke that you can go up to before, you're physically loading a screw with a force. And at some point, it's just like a column, so that screw can only handle so much before it runs into a buckling limit. Similarly, that kind of correlates to the moderate force. One thing I've seen in the linear servo industry as technology continues to advance is kind of this push upwards in the force range. So, previously you may have been able to get up to, 40 tons. Now we're seeing 50 tons and well above, up to 150,000, 200,000 pounds of force. So really depends on, the manufacturer, the life cycle you want to get out of the unit, and quite a few other perspectives there. But that technology continues to advance and continues to push upwards into the force ranges. So if you take away nothing from this slide, then this, I'm not saying, hydraulic and electrohydraulic don't have their place. Absolutely do. Each one of these technologies is a key piece of automation, and they really need to be evaluated based on your specific application. So kind of in general, I got the picture on the right, and that's really more focused on a traditional linear press application, but press applications exist in a whole variety of situations. So you could have even something from you want to press a billet of metal into an oven or something like that and compress that when it's being heated. So kind of think outside the box, not just this traditional kind of C-frame press that you see here. On the press technology side, and this is regardless of the technology you pick, hydraulic to linear servo, there's some basic information that you need to collect. And that's going to kind of start drilling down and dictating not only what technology you use, but if you're going the linear servo route, what we need to think of from a sizing standpoint. So, obviously the biggest one up front is how much force do you need? That's going to dictate the basics of, your hydraulic pressure unit, your size of hydraulic actuator, Similarly, over to the linear servo side, that's going to dictate how big of a screw you need, how much force you can get out of that specific actuator. Duty cycle, that's another important one because there are a couple different key technologies, especially in the linear servo space. You may have some low duty cycle actuators. They're much cheaper. They have lower service life than a high duty cycle actuator like Tolomatic makes. But if you have a press you're only using a few times a day, that might be the appropriate technology to take a look at. The other piece here is your target press cycle rate. So that's how many times you want to press in a given minute. And a lot of that plays into the sizing that we'll get into in a little bit. And then tooling mass, that's important to consider because you're obviously asking the actuator to carry that mass up and down or left to right, depending on how you're orienting it. And then target equipment life cycle. And that's really applicable to more of your linear servo when you get into the screw characteristics, because one of the things we'll talk about is, screws have a traditional statistical expected life. So it's a lot easier to have a predictable life when you're specifying the equipment up front. And then on the right side, this is more general system information, and this can apply to any of the key technologies for pressing. Tooling guides, hydraulics can generally handle a lot more side load. With electric, you might need to consider putting some kind of guides along the tooling to make sure you're not imposing a side load on that rod end. Preferred control system, that's again going to be largely based on preference, based on what you're used to, based on what you need that control system to accomplish. Environmental factors is another big one, and that really is more going to impact your linear servo. If you need a specific IP rating, like you're in a very dusty environment where there's a lot of sawdust or something like that, that may really drive you towards selecting an IP67, or you may be in a washdown application, and you might want to look at, a stainless steel or IP69K for washdown. And this last piece wasn't put last for a reason. You'll see that in kind of the upcoming slide, but safety considerations is a really key metric that you need to be considering on each one of these factors when you're designing a press for your application. So, the basics that everybody kind of thinks about are light curtains, overload protection, and then emergency stops. Those are kind of the basics, but you can even work backwards insofar as some of the technology you're considering. How does that impact safety in motor choices? Are there certain safety features like safe torque off that you need to consider implementing? So that's kind of a common theme you need to be looking at across the entire system. So why might you consider, transitioning towards a linear servo press versus some of the traditional technologies? Well, the most obvious and the one that pops up most frequently, at least for us, is really environmental factors. So there's, as I'm sure most of you have seen, a growing development within the industry and within the regulatory bodies of, reducing the presence of oil in automation. And there are some customers that just want to get away from that, either from a predictable life standpoint, from a potential material incompatibility standpoint, such as the medical device manufacturers I have highlighted here, or other folks. You can get a lot more repeatable production out of servo electric press. So that may reduce your scrap rate. So they're really looking for that consistent throughput product. Cost factors, and there's a lot that you can go into on this setup, but when you're evaluating between the technologies of press systems, you need to dig a little farther past just the upfront cost. So that's your initial purchase price upfront. If you're looking at the hydraulic system, it'll be a hydraulic actuator plus the hydraulic power unit, and that hydraulic power unit may drive multiple actuators in itself. So you may end up with a smaller overhead cost on initial purchase than you would on a traditional electric servo press. But behind that, you got to look at the hidden costs as well. For example, touch on this in the first slide. The energy efficiency of hydraulics is probably about half of that of the electric counterparts. So that's going to be one thing where you can effectively put together, real-time cost differential on use over a year and look at your actual return on investment in savings for energy efficiency. So that's a potential there. Downtime and service, those can be generally estimated based on historically what you've done on the hydraulic side in the past. Generally on the electric side, if everything is sized and specified correctly, again, you should have a predictable life out of the unit, and you can much better plan for downtime and repairs. So in general, kind of to wrap that up, total cost of ownership. So that's what I'm kind of driving at here. Really makes sense when you're looking at, a dedicated HPU or hydraulic power unit that's only driving 1 or 2 cylinders. So you're spending a bunch on the HPU, it's only driving 1 or 2. That total package cost is pretty high. Mission critical applications. Again, that goes back to more of the reliability aspect and making sure that or at least have an idea of upcoming issues in your application. And then key precision and control applications. That is one spot where your linear servo press has a distinct advantage, because there are a lot of opportunities for you to take a look at increased precision and accuracy, whether it's based on your screw selection, which we'll get into in a little bit, or just overall speed and throughput that you want to target. So, those are probably the areas that it makes most sense to really target the linear servo press. Going back to that first bullet, if you have extremely high forces with a single HPU that's running multiple hydraulic cylinder, it may not make sense to take a look at linear servo press technology in that application. So just something to keep in mind. So we touched on this a little bit as well, but the linear servo press benefits, the biggest upside that you're going to get here, improved process control. And you get this a little bit with some of the electrohydraulic technology, but you get much more precise, repeatable motion. It's going to be a lot less affected by temperature and other external factors. So whereas you may need to account for that in a hydraulic system when you get to low or higher temperatures, the electric system is not going to be quite as susceptible to those. Generally, since we can program this to precise movements and limit the amount of unnecessary motion you have to do, you can take a look at setting up your programming so that you can reasonably increase your throughput on a traditional machine. So instead of going back and forth full stroke, you may only have to come down and operate in this range before you go back up. So there are some benefits you can have there. And then kind of highlighted this on the top here, but that data collection piece, that's really a growing field, not only in the servo hydraulic, but also the electric side. So now that you're starting to run things with a servo motor on both the electric and servo hydraulic, there's a lot of data you can get out of those pieces of equipment. So anything from, current trending, so you can start to see if things are operating differently than they might have when you installed it. That's an indication that either something's changed in the application, or you may be seeing some additional wear on some components. So some of that you can use to look at some preemptive monitoring and plan for some repairs ahead of time. So really what we're trying to drive at is, less machine downtime, and then less maintenance and replacement costs of having to rush equipment in versus having a little more predictability on that life. So focusing more in on the linear servo press design process. And again, I'm not going to go through everything here. We're mostly going to touch on the first two, quickly touch on the motor and drive, and then the mounting and frame. That largely gets into more of a machine builder and evaluation of structural strength and space constraints. So I just wanted to put this up here, and you'll notice on the left-hand side there, safety considerations, like I mentioned before, really should come into play during your entire linear servo press design process. So on the initial piece, I'm sure as many of you are familiar with, it's the basic forces and loads, basic cycle rates, duty cycle, stroke. If you have any kind of performance requirements you need. Kind of the next step is to move down to that linear actuator selection, because at the root, the linear actuator is going to be doing the brunt of the work of the linear servo press. So you kind of start at the base, and then you move outward to the motor and drive, and then you may move outward to the mounting and frame. So in general, again, this is a little bit of a copy of the last slide, but I wanted to lay this out so you kind of see what you need to look at. So the tooling weight and press force, the motion profile, which you're really going to be looking at cycle time, dwells, and here's a key one that I see quite a few people miss is your approach distance and your press distance. And we'll get into that in the press move in a second, but that's a key thing to remember here. And then after you have identified those first two buckets, where you actually apply those loads and forces is going to be pretty important for sizing a linear servo actuator. And last but not least, these can be used in a reputable sizing software. We at Tolomatic have SizeIt that's readily available. I know there are other linear actuator sizing programs out there, and we've got folks that do them by hand as well. So it's kind of up to you at that point. Like I said, the press motion profile, this is the thing I wanted to get into with the two different moves that I was talking about. So keep in mind, this is not necessarily going to apply to every press situation. You may have a punch or some kind of similar press-ish application that you want to get to a certain speed and then hit a piece of sheet metal or something like that at that speed. So this wouldn't necessarily apply to that, but this is going to be more for your traditional press units. So you got your press approach, and it's important to note that that is the tooling weight only. And then really want to identify that actual working stroke that you're doing the press over. So that's your press motion there. And that's going to be your applied press force as well as your tooling weight. And the reason I stress this so much is a lot of times I see folks go through a sizing exercise and they apply the press force to the entire movement. And a couple things that are going to be problematic about that. One, we're basically telling a sizing software, or if you're running it by hand, telling the calculations that you're doing a lot more work than you actually are in the application. So that's going to basically produce higher perceived requirements for the actuator and motor than you actually need. So you may end up overspecifying your system. The second thing is, especially on the motor side, your RMS torque, now you're operating at that force over the whole range, that's going to be incorrectly calculated high. So again, we really want to kind of dive in and figure out what's going to be the best fit for your specific application based on how you're going to use it. So a couple key pieces of the best practice here, again, if we're slowing down into the press, that's going to decrease shock load on the actuator. Linear actuators, especially roller screws themselves, can take a reasonable amount of shock load, but in general, best practice to limit that wherever possible. Extends equipment life. And then, like I mentioned before, that's going to help you right size your motors and basically not overspend on your initial purchase and find out you could have gone a size down later. Screw technology, those of you who have joined some Tolomatic webinars in the past have probably seen a variation of this slide, but this is important when it comes to press applications in particular, so I wanted to highlight this. The basic screw technologies that I generally see used in an application with pressing are going to be your ball screw and your roller screw. And this is where you kind of start to drill down into, for your application, what do you need? Now, I know I have pressing on the roller screw, and that's very accurate, but not every press application needs a roller screw. So for example, if you're doing a press over a relatively long distance and it's within the capabilities of a ball screw, you may be able to get a little bit cheaper option that will still have sufficient life for your needs. On the flip side, if you're doing a press in a very small or short stroke, I would highly recommend you look at the roller screw. And the reason for that, you can kind of see here on the pictures. If you look at the ball screw on the left side, you see how there are really only 2 points of contact where that ball is meeting the nut and the screw. So if you operate on a very small stroke with a very high force repeatedly, now you're point loading the same ball over and over and over again, and that may lead to spalling and fatigue on your ball screw and premature failure. So in those situations, generally we're going to move over to the roller screw. For the same package size, you're generally going to get much higher thrust output and a much longer life. So you can see on the right-hand side there, with that cutaway of the roller screw, instead of moving just between 2 points, now we've got a very large surface area of contact, so we can distribute that force across the entire screw and nut. So that's really what we're looking for when we're doing those very short press motions. And generally, I like to look at that for motions that you're within 1 revolution of the nut for a press application. Final actuator selection. So say you've kind of taken a look at the sizing. Any actuator company is probably going to spit out quite a few actuators that can actually fit into an application technically. This really comes down to acceptable trade-offs. So you'll see on the bottom there, I've got a number of different actuators shown. In the middle there is our high force RSX that can go up to 66,000 pounds force standard, and we've looked at higher options in the past. So you may not need that if you're only pushing 2,000 pounds of force, but technically it'll fit. So here's where you want to start looking at based on my performance criteria and what life I want to get out of that. I need to balance those with the cost and sometimes with the package fit, especially if you're replacing a hydraulic unit. So this is a really great opportunity for you to do a little background research on the actuator options available to you. And definitely from a Tolomatic standpoint, give a call in and talk with an application engineer to discuss this in a little more detail. So most vendors should be able to help you identify a little better and narrow that down to a couple actuator options. Again, just touching on this real quick. So the motor selection overview, most reputable sizing softwares, or if you do this by hand, you're going to have outputs of motor requirements. So that comes from the actuator manufacturer. A lot of folks I've seen use this as a reference and then do their own motor specific sizing based on the motor vendor sizing software. So that's always a good reference point just to kind of make sure everything's calculating roughly equally. But from a raw data standpoint, these motor requirements are what you're going to need to meet at a minimum. And again, to bring this back to the safety aspect, you also need to be thinking about, safety functions. Do you need STO? Is there a certain kind of feedback device you need? We've seen folks do safe feedback devices in the past. You may have an application that is more of a punch application, so there's a lot of vibration and shock load. In that situation, you may want to use a resolver or something that's a little more conducive to shock. And generally, it's going to be, what's the ease of integration path for you? So a lot of folks have their preferred motor vendor. That's great. The other option is, for example, the Tolomatic IMA or integrated actuator. Some of those exist out there that can come with a manufacturer specified connector on them and connect straight up to a third-party drive. So there are a couple options you can go with on the motor front. So to kind of bring this all back in summary, first thing that I hope you got out of that first slide was, all press technologies really play roles in automation. There's not necessarily one that is distinctly better for every application. So you really need to critically think about what you need to do and what your performance requirements and costs are before kind of going down one of the routes of the different technologies. Second thing I want to make sure we highlight here, linear servo presses, they're very strong in critical applications. So again, there's growing environmental needs. A lot of end customers are moving that way or would like to. The technology continues to advance. So higher forces, longer strokes are becoming more and more feasible. And, for reference on the long stroke, I've seen things anywhere upwards of 1.5 meters and above as potential press solutions that have come across my desk in particular. Reduced downtimes and maintenance costs. Again, that real-time data you can get from the motor and drive is pretty vital in that. A lot of people have that, and it's tough to know how to use it. So spending a little time familiarizing yourself with the system can go a long way generally. And then increased performance in key critical applications, and that predictable service life are another couple drivers for this. So kind of wrap up, the linear servo press sizing, hopefully kind of that quick walkthrough. It's relatively straightforward. Our sizing software, you can walk through a specific press motion profile, and it should kick you right out to a couple options for you. Otherwise, get in touch with Tolomatic or your local distributor or your preferred vendor, and they should be able to help you out with it. So with that, I really appreciate everybody jumping on and spending their sometimes lunch hour with me. So I guess, Chris, do we have any questions? All righty. Well, with that, I think we're going to wrap it up. So thank you again, and we'll see you next time.